In this video, we're going to talk about the discrete logarithm problem from a mathematical perspective. All right, so let's begin by talking about the definition of a group. And to understand the discrete logarithm problem in general, we really need to understand what a group is. The concept of a group is really a cornerstone in mathematics, and groups are studied in a field of math called abstract algebra. So let's talk about the definition. We let G be a non-empty set, and star is a function from G cross G to G, and it represents a binary operation on the set G. If we're given two elements of G, the image of A comma B, which is an element of G cross G, the image of that point under star, we denote it as A star B. So given any two elements of G, A and B, we have this associated element A star B, which is also an element of G. Now this structure, G and star, is going to be called a group if it satisfies the following three conditions. First of all, the operation star has to be associative, which just means for any three elements, A, B, C, and G, that if we do A star B first and then star C, that's the same element as if we did B star C first and then A star with that. We also demand an existence of an identity element, which we denote as E, and all that means is that if we take any element A, that A star E is the same as E star A, which is A. And finally, to be a group, we need the existence of inverses. So for every element A and G, there must exist some other element B and G such that A times B or A star B equals B star A equals E, the identity. Now, this definition here doesn't demand that the operation be commutative. And for the group to be commutative means that for every A and B and G, that A star B is the same as B star A. And when this is true, we call this an abelian group. The term abelian comes from the mathematician Abel. He's a Norwegian mathematician known for his work on proving that the fifth degree polynomial is not solvable by radicals. And he died quite young, actually. And the fact that we write abelian with a lowercase a is actually a great honor. So all the groups that we consider here will be abelian. So we could say commutative groups, but it's more standard to call them abelian groups. Also, a very basic definition is if the group is either finite or infinite. And that just means whether the underlying set G is infinite or finite. So if G is an infinite set, we are going to refer to the group as an infinite group. If the set G is finite, then we call it a finite group. And in the case of a finite group, the order of the group is just a cardinality of the set G. And in this video, all the groups we consider will be finite groups. Now, a fundamental example of an abelian group is the set of integers under addition. Usually we write the set of integers as z, and the operation we'll just write as usual as plus. So plus can be viewed as a function from z cross z to z. The identity element is 0, and the inverse of an integer n is minus n. And since addition is commutative, in other words, a plus b is b plus a for all a and b, we see that Z is an abelian group. Now, Z is an infinite set, so this is an infinite group. Notice, though, that if we try to consider Z under multiplication, then it's not going to be a group because inverses don't exist. For example, if we take the number 2, there is no value of n for which 2 times n equals 1. 1 is the multiplicative identity. So for 2 to have a multiplicative inverse, we would need to find some element of the set Z such that 2 times n is 1, and Although n equals a half works, that's not an integer, so that's why we say that 2 does not have a multiplicative inverse in Z. Now, the next important abelian group to consider is Zn, which is really just a set of residue classes modulo n. So we can regard n as the set of integers 0 up to n minus 1. So now, under addition, this is an abelian group, and the cardinality of this is n. This is a finite group now. There's n elements in it, and we see again that although Zn is a group under addition, it is not a group under multiplication, because multiplicative inverses don't always exist for all of its elements. But there are a lot of elements in Zn which do have multiplicative inverses. They don't all, but a lot of them do. So which elements have a multiplicative inverse? Well, remember that if we're given two positive integers a and n, there's going to exist an integer x that satisfies ax is congruent to 1 mod n if and only if the greatest common divisor of a and n is 1. So an element a in Zn will have a multiplicative inverse if and only if a is relatively prime to the modulus. In other words, the GCD of a and n is 1. So why don't we just restrict our attention to those particular elements? Let's define Zn cross, or people often write as Zn star, to be all the elements a and Zn which have the property that the GCD of a and n is 1. Now, in fact, Zn will be a group under multiplication. The multiplicative identity is 1, and the cardinality of that group is going to be phi of n, where phi is Euler's Totient function. Just remember, phi of n is the number of integers in the set from 1 to n, which is relatively prime to n. And an important special case of this group is when n is a prime. So we consider ZP cross. The reason this is important is because every element a from 1 up to p minus 1 is relatively prime to p. So here we see that ZP cross is a finite abelian group, and the order is p minus 1. We can think of ZP cross as just the set of integers, the finite set of integers from 1 up to p minus 1. And this is a abelian group under multiplication. And these particular groups, in fact, are very important in cryptography. Now, another very important class of abelian groups that are important to cryptography is found within elliptic curves. So if we take a prime number p larger than 3, and two elements a and b in ZP, we can define the set of points xy tuples in ZP cross ZP, which satisfy this equation y squared equals x cubed plus ax plus b. As well, we adjoin a point at infinity. Now, provided the discriminant is non-zero, the discriminant being this value negative 16 times 4a cubed plus 27b squared, as long as that's not zero in ZP, which is just another way of saying that 4a cubed plus 27b squared is not divisible by p, then that set E, a, b, comma, p, is actually a finite abelian group under a certain binary operation, which we won't talk about in this video. I did some other videos about that. Now, under this operation, which we denote as plus, we have an example of a finite abelian group, and this particular group also plays a very important role in cryptography. So when we look at specific examples of abelian groups in the real world, we see that sometimes the abelian group uses a plus for its operation, and sometimes it uses a multiplication for its operation. So in other words, the binary operation star is sometimes denoted additively with the plus symbol, and sometimes it's denoted multiplicatively with a dot. So we've seen this. ZP cross uses multiplication, so we use a dot to indicate that operation, whereas for an elliptic curve, it uses plus for its operation. Now, really, the distinction between abelian groups using the additive notation plus or the multiplicative notation dot is really just a notational inconvenience, and there's no real serious significance to the difference there. They're the same thing. So let's keep that in mind and see how these definitions go here. Let's take the two cases where we write our abelian group with plus and with a dot. So additive notation versus multiplicative notation. So with the additive notation, if we take any two elements of G, A and B, the value of the group operation will be A plus B. And for multiplication, if we take any two elements of G, the value of the group operation would be A dot B. Same thing though. Now we want to define the concept of repeating an operation on the same element k times, where k is some positive integer. And under plus, k times a, we're just going to define that as a plus a plus a all the way k times. And in a multiplicative notation, we'll kind of use an exponent to denote that. A to the power of k, by definition, will be a times a times a, k times. And these are the same thing. It's just a different way to write it depending on whether we're using additive notation or multiplicative notation. And for convenience, let's also consider the case where k is 0. So when k is 0, 0 times a is just the identity element e. And in the multiplicative case, a to the power of 0 is the identity element e. So these are the same thing. This is the point. Now, to move on, we need to talk about what a cyclic group is. So if we're looking at an abelian group using multiplicative notation, to be cyclic means that there's some element G in the group such that every element of G can be expressed as a power of little g. So in other words, given any element x in G, x is going to be equal to g to the power of k for some k greater than or equal to 0, some integer k. And very similarly, no real difference if we're writing our abelian group with additive notation. For this group to be cyclic just means that there's some element G in G such that every element x can be written as x is equal to k times G for some integer k greater than or equal to 0. Now, regardless if we're using additive or multiplicative notation, such an element G is called a generator, and it's also called a primitive element. So just to summarize that, so if we have a finite cyclic group using multiplicative notation, and the generator is lowercase g, that means the set capital G is just the powers of g, g to the k, where k ranges from 0 to n. When k is 0, we get the identity, right? G to the power of 0 is the identity. And then the other elements are proper powers of g. And if we're using additive notation, then the set capital G is just k times g, where k ranges from 0 to n. Exactly the same thing. All right, we're finally ready to talk about the discrete logarithm problem in general. We'll denote that as DLP. Whenever we talk about the discrete logarithm problem, there's always a finite cyclic group in the background. And why don't we explicitly state the exact formulation of the discrete logarithm problem for both the additive and multiplicative notation. So the discrete logarithm problem for additive notation, let's take a finite group, and let's say the generator is G. And in the additive case, G is k times G, just like we saw, where k ranges from 0 to n. And what is the discrete logarithm problem there? Well, we know that every element of G, every element x of G is of the form k times G. So if I give you an element x, how do you find that integer k, which lies between 0 and n minus 1, such that x is equal to k times G? That's the problem. Remember, lowercase g is fixed, but x is an arbitrary element, and if such an element is presented to you, how do you find that value k, which gives you the value of x? And very similarly, for a multiplicative notation, we have a generator lowercase g. Every element of capital G is a power of little g. So if I give you some element x in G, how do we find that value of k, which satisfies x is equal to g to the power of k? And these are the same problems. There's no difference here. It's just a notational difference. But other than that, there's no real difference. Now, remember that we always know k exists, right? No matter what value of x we're given, either x is equal to g to the power of k or k times g, depending on which notation we're using. And we could try to find k just by brute forcing, which means just keep trying values of k starting at 0 and 1. And technically, you will eventually find it. But the point is that in practice, the size of these groups is so large that even if you try to find the value of k using a cluster of supercomputers, it's going to take you an extremely long period of time, as in decades or centuries or whatever. So it's in this sense the value of k cannot be determined, even though it exists. And the intractability of solving for k is really the basis of the discrete logarithm problem and the basis for the Diffie-Hellman key exchange. We won't talk about the Diffie-Hellman key exchange in this video. We're just going to focus on the discrete logarithm problems. So whenever we want to talk about the discrete logarithm problem, we always need a cyclic group, a finite cyclic group, to be in the background. Now, ZP cross is a cyclic group. This is not obvious. It requires a proof, but it's true. Given a prime P, it's actually not obvious how to find the generator G, which generates the group. Sometimes 2 works, but it doesn't in general. Now, as for the elliptic curves, E of A, B, P, this group is not always cyclic, but it is very often cyclic. And if we can find some specific values of A, B, and P, for which the elliptic curve E of A, B, and P is cyclic, then we can consider the discrete logarithm problem for that group. Whenever we have a finite cyclic group, we can always consider the discrete logarithm problem for that group. So why don't we pose the discrete logarithm problem for the cyclic group of the elliptic curve and for ZP cross side by side and see how that looks. So in the case of an elliptic curve, which uses additive notation for the group, let us suppose we have a prime P and 2 values of A and B such that the elliptic curve that corresponds to those parameters is cyclic. It's not always, but we can find such values. And why don't we let capital N be the size of this group? What is the discrete logarithm problem for that group? Well, we would like, given any element x and e, we'll let G be a generator. Given any x and e, how do we find the value of k such that x is equal to k times g? It's really what we said before. And for the specific abelian group ZP cross, which uses multiplicative notation, how does the discrete logarithm problem look there? Well, we're given a generator G, and any x in that group, there should be some value k such that x is equal to g to the k. And the problem is, how do we find that value of k? Now, to get a sense of how large the numbers are when we actually look at some real-world problems, let's take a look at this. If we look at the website CryptoPals, if we look here, we see that here is an example of a prime P and a generator G. So in this case, G equals 2 generates the group. It doesn't always, but in this case it does. So these are 2 parameters, P and G, which are used in real-world cryptography. And we see how large this prime is. This prime is in hex right now. If we change it to on base 10, this is the prime. So we see that how extremely large a prime is used in real-world applications of ZP cross. Also, we could look at a real-world example of elliptic curves. So why don't we take a look at this document here. On page 22, we'll see an example of a curve that they use in real-world cryptography. Let's take a look at this curve here, P224. So the prime P that's used in this is this value. The size of the group is this. The value of a is -3, which is just the same thing as this value. It's actually just 3 less than this number. And the value of b is this large number here. So we see that, and the generator, g is a tuple, right, in elliptic curve, so we need to specify both the x and y coordinate. Here they are. So this particular value generates the entire group. We see how large these values are. They're crazy, right? There's no way we could do a brute force search on this and hope to find the value of k that we're looking for to solve the discrete logarithm problem. You know, just to see maybe how you would even try this. It's ridiculous, but we can write it down. So let's take the prime p that was specified there, and we'll make up a value of x, let's say 2020. And remember, our generator g is 2. So there should be some value of k such that 2 to the power of k equals x. And if we try to write a little for loop trying to find that, we can try it. But the point is, it's the value that we're looking for, k, is so large that this for loop will just never end. Even if we use very powerful computers, it'll just take too long. And it's in that sense that the value of k cannot be found, and that provides the security. All right, so I just wanted to talk a little bit about the discrete logarithm problem in a general sense, and trying to contrast both the case of elliptic curves and ZP cross. And both of these are used in the Diffie-Hellman key exchange, which we'll talk about in another video.